But anyways, my name is John Adkins. I'm here today to talk about carbon fiber reinforced polymer and FRP condition inspection. This presentation is a little not quite as exciting as the drone presentations as earlier, but I think it's important. So everybody probably knows what FRP or carbon fiber looks like. It's, you notice it from its common kind of weaved appearance. We have a lot of exotic applications for it nowadays. In this instance, rims. Some of you may have these, probably not. They're $14,000 if you're interested. And Shay had a picture of a Ferrari yesterday, and I do too. This one's made out of carbon fiber, and it's $1.9 million. Next up is toilet seat. If you build it, someone will buy it. This is $400 carbon fiber toilet seat. Tripods, a lot more common applications. You know, some of us probably do have these. It's a high strength, lightweight application. That's what carbon fiber is designed to do. It's expensive, but it's high performance. Bicycles, some of us may have these. They're high strength, high performance, and kind of expensive. And they do break. So what is FRP, and more specifically, carbon reinforced product or polymer? Fiber reinforced plastic or polymer, FRP, as we commonly know it, is a matrix consisting of fiber encapsulated in a polymer or resin. Carbon fiber, which most people consider FRP, but it's more specifically carbon fiber, a strong material that consists of thin fibers made up largely of carbon atoms that are bonded together in microscopic crystals. That's a mouthful. It is very useful for applications needing high strength and low weight. The fibers that you use in FRP, whether it's carbon, which you make carbon fiber out of, glass, you know, which fiberglass, and aramid, which is typically Romex or Kevlar. Most of what we'll be talking today is carbon fiber, because that's mostly what we've used on the structural side in Oregon, and I think most structural applications. But we do have a few examples of FRP and fiberglass decks, or actually bridges. With FRP, the polymer or resin provides the stability and the shear strength and bonding of the FRP to the substrate, while the fibers provide the strength. So it looks good on, you know, an overpriced bicycle or golf club or a tripod, but what are we doing putting on bridges? I know the first project I worked on where we actually installed FRP onto a retrofit, I kind of, you know, thought, wow, what is this? This is just an expensive Band-Aid. How could this possibly give us strength? But it does. We use it for increased load demands, as Shay Burroughs mentioned yesterday, with different load combinations on our older structure. We're kind of, as agencies, we're kind of in a pinch. Most of our bridges aren't, you know, may not meet new load capacities or load demands. So we have to do something. So we can increase them in flexure and shear using FRP. Also deterioration of existing members. When we have high load hits, abrasion, a lot of piling in kind of the southeast Florida area where you have saltwater deterioration, you can actually there's a lot of different fixes for deteriorating members. And in seismic retrofit, as we saw in Hawaii in our previous presentation, you can use it for seismic retrofit. So with increased load combinations on aging infrastructure, we find more and more structures that don't load rate out. Do we tear these bridges down or retrofit them? In most cases, these bridges that don't load rate out anymore are in good condition. We don't see any excessive structural deterioration. And so it seems like most of these are good candidates for retrofit. Traditional means of retrofit consist of increasing the reinforced concrete section, adding steel plating, external PT or post-tensioning, and many others. Carbon fiber reinforced product or polymer gives designers a new means of increasing shear and flexure capacity, which doesn't change the member sizes and is faster than most other methods, and which usually translates into cost effective. So, deterioration of existing members. When a structure is damaged from a traffic hit, reducing the capacity, we can use this as a tool. Typically concrete, also in concrete spalling, as mentioned before, reduces section size, such as underwater columns. We can use this as a tool as well. Rebar corrosion, causing reduction in capacity. Here's a picture of a high load hit. I think we've all seen this. Usually it's just a matter of restoring either the post-tensioning or the reinforcing bar section, reconnecting that, recasting the concrete section that's been deteriorated or lost. And FRP actually, and you can actually add FRP. We haven't done it in Oregon, but I know states do to kind of further strengthen that repair. And it's usually the trucker's insurance is paying for it, so hey, might as well use FRP. Here is a picture of deteriorated columns. I think PileMedic is a company, a proprietary system that's been out there for a while. They use it for wrapping a deteriorated section, whether it's timbers, concrete, and they're not the only company. So for seismic retrofits, I don't think we've used this in Oregon that much, but I know many other states have. It essentially acts just like a steel wrap or spiral reinforcement. It just contains, or confines a otherwise under reinforced, concrete column. So it's a pretty good option. So now I'll talk a little bit about the history of FRP and civil engineering. FRP was first invented in 1905 as Bakelite. Basically, it's the invention of plastic. Carbon fiber, as we know it, first came into existence in the 1960s in Britain. In 1970s, world polymer production or plastic production surpassed that of steel. So it's not going away. We're only going to see it more as it replaces our traditional materials. Carbon reinforced product was first used in a structural application in the US in the early 1990s, although I believe it was used in Europe and I think Japan and is in the 80s. So carbon fiber in Oregon. The first ODOT project was in 1998 at the Horsetail Falls, and some of you in the room may have been involved with that. Since then, we've applied it to over 40 state bridges, many local agency structures, and within Oregon. The majority have been installed in the past 5 to 10 years, and most carbon fiber strips were installed using the wet layup method, as we'll talk about later, which increased either the shear or the flexibility. We do have a few new NSM or near surface mount installations at FRP, and we'll talk a little bit more later in this presentation about that. We do have several FRP decks. It's not carbon fiber, but it's a fiber reinforced polymer deck. I'm sure many of you in the Northwest have read about some of these. We'll talk about that in a bit. We've had mixed results. A few have worked, some of them haven't. And we actually have, I don't have it on the slide here, but Oregon State Parks actually has a fiberglass bridge that they use. We won't talk much in this presentation about the installation or the inspection of fiberglass, as it's pretty uncommon. But the rest of this presentation will cover just the installation and inspection of carbon fiber, using the wet layup method. So in Oregon, we have a lack of a long-term performance history of carbon fiber. In the US, it's only been around for almost 20, 30 years. So that kind of goes for the industry in general. It's for structural applications. Typically, it's located in hard-to-access areas of bridges, on non-fracture critical members that require equipment to inspect hands-on. However, so it's hard to justify a really hands-on, in-depth inspection of most of this material. There are no current state or federal regulations to, get a snooper every time you look at that old reinforced concrete bridge. So for that reason, and several others, I think we don't have a real grasp on how this material is performing across the board. We stand on the ground, we look at it, and if it's stuck, we assume it's holding. But there's more to it, and that's the point of my presentation. In Oregon, we have a lack of generally accepted construction specs or process control procedures due to the rarity of projects and kind of the proprietary nature of this material. ODOT's currently trying to work on a standard to get more uniformity in our FRP, or carbon fiber retrofits. With the carbon fiber retrofits in Oregon that we do inspect, we've noticed many minor construction deficiencies, and we've noticed a few major deficiencies, such as debonding. But for the most part, they're doing what they're intended to do. FRP decks have had very poor performance. So now I'll talk a little bit about where we have used it and specific examples on the state side. So as mentioned before, Horsetail Falls, this was our first project. A little brief around the bridge. It was built in 1918 at a cost of $1,817. So if my math is correct, that extrapolates to $43,000 today. So bridges were a little cheaper back then. So the bridge was rated. This is a historic structure located on the Columbia River Highway. And the bridge was rated and it only had 7% of required shear and 50% of required flexural capacity. So we had to do something, but as a historic structure, we didn't want to tear it down and we didn't want to significantly alter its appearance. The condition of the structure was still good. The concrete was sound, and we didn't have any excessive rebar corrosion. So this was the perfect candidate to try out a carbon fiber retrofit in Oregon. OSU, which has worked, hand in hand with the ODOT for a long time and has been a good partner, they mocked up the girder section in their lab. They applied the carbon fiber retrofit that we were planning to use on the bridge, and they tested it, and it proved that it indeed increased our shear and flexural capacity to required levels. So we went ahead with the project. Here's another example of most of where we see carbon fiber retrofits in Oregon. It's a older, reinforced concrete structure, built in the 50s or 60s. It's still in good condition. There's no reason to replace it. However, it isn't rating out anymore due to increased loads. So we spend a little bit of money and we get a lot more out of this structure. Seems like a pretty good use of our dollars. Another example similar to the previous. This is an older reinforced concrete structure covering a large span. To replace this structure, it would be a significant cost to modern standards, given the remote location. So carbon fiber gets a lot more life out of this perfectly good concrete structure. Another historic structure, just like Horsetail Falls, a lot of our historic structures that don't rate out, we don't want to alter their appearance. So this is a pretty good fix. Looks like they they strengthened the floor beams on this structure for most likely shear. Here's kind of an odd example. You probably don't see a lot of these. This is some carbon fiber that was added to a reinforced concrete girders. They were placed over timber substructure elements. Typically, you're not going to see carbon fiber in this application because, anytime you have timber in substructure, it's probably at the end of its service life. So, yeah, I'm sure there's a good engineering reason for this, however. More of the same, smaller, older reinforced concrete bridges, kind of in remote locations. Didn't really justify, we could throw a little bit of carbon fiber on it and get more life out of it. More of the same. Looks like you can tell in the appearance from these pictures that you can see the girders were strengthened with carbon fiber. So as most of us have probably inspected carbon fiber material on our structures, you can always tell where it's at and kind of the configuration of what it's intending to do. You can see we have some shear strips, probably some flexure strips on the cross beam or your cap, and it looks like we have shear strips on our girders. You'll see the strips and you'll typically see the paint. For whatever reason we didn't, it looks like on this bridge we strengthened the girders and not the cap. And a lot of our bigger structures, the steel main spans are just fine, but the approach spans are not rating out. So carbon fiber is a good option. We have thin shear strips that were installed. This is in Eugene on the Willamette River Bridge. Here's an example of near surface mount. We don't see a lot of these, but they are out there. This in the lower right hand corner picture, you can see where we've cut an inlay or cut a groove in the bottom flange of our reinforced concrete girders, and we've epoxied and inlaid carbon strips. So that's considered near surface mount. So we've installed this for flexure strengthening. Here's kind of an odd example of something on our Oregon inventory. This is a near surface mount deck rehab that was installed out of Eugene, but it's actually installed on the top of the deck underneath the sidewalk, most likely trying to strengthen the deck section for the rail retrofit. So in the event that a car hit the rail, the deck section is going to be able to carry that impact force. The downside to this detail is that we're unable to inspect this NSM because it is covered underneath by the sidewalk and the wearing surface. And here is kind of an oddball. This is provided by Katrina Cam from State Parks. So this is a fiberglass bridge. Technically, it's FRP. We don't see a lot of these. I'm not sure how they deteriorate because we don't have a lot of them on the inventory or history of it. But it's perfect for the state parks and kind of what they're trying to achieve with their structures. This is a bridge that you can carry carry the components in by hand. And so when you're in remote locations, in remote trails in the state park system, they can get this material in for fairly cheap with their crews assembling on site, and no roads or helicopters are required to get the material in. I think sadly this bridge was taken out by a flood, but they have more in the works. And the Forest Service also has used these for many structures. I mentioned I'd talk about FRP bridge decks. This is the Morrison. This is the one that you probably have read about in the news. It's got a sordid history. The old grid deck was replaced in 2011 with a prefabricated FRP deck panels. The fasteners between the FRP panels and the stringers started to fail in 2012, right after installation. The county, after a long, drawn-out, lengthy court process, the county, contractor, and the supplier finally came to a settlement. of $4.4 million in damages in 2015. And the deck is scheduled to be replaced with concrete-filled steel grid in 2017. So it's a good idea, but it didn't work in this application, unfortunately. Here is another structure. It's kind of the same story. The old Youngs Bay bridge deck. It's located in Astoria. It was installed in 2002, which may have made it one of the first FRP decks in Oregon. I'm not sure. Similar to the Morrison, shop splices and attachment to the stringers failed, and it was replaced with a steel deck in June 2010. We do have decks that have not failed catastrophically. The steel bridge in Portland that was installed at the same time as the Morrison, that's still in service. We've had some issues and some repair associated with it. But proponents of FRP bridge decks will say that it's still a good process and the panel is a sound idea, but it's just the connection detail that needs to be worked out. So we may see more of them, or maybe not. So now we've kind of talked about what FRP is, where we've used it, why we use it. Kind of talk a little, now let's talk about what we do to inspect it. The use of FRP retrofits on a bridge is increasing. These retrofits are a critical member. That's what's important to note as inspectors, that it seems kind of like a benign element that's just stuck to the side of our girders, but it is a critical member, and it's keeping, and in some cases, or if not all cases, it's keeping that member from being load posted. So it is something that we need to pay attention to. So what should we be looking for during inspection? There isn't a long-term record or institutional knowledge of its performance on bridges. So before we inspect it, we need to try to get the most basic information on what we're inspecting. Prior to your inspection, you need to gather information. You probably can get a hold of some plans, product info, maybe you can get a hold of this. Installation procedures, these are all like important documents and kind of help you in your field inspection. What material was used, different systems have different inherent problems, what resins were used, QA, QC documents, these are pretty invaluable, but good luck finding them. They're probably buried somewhere. But you usually can get the plans. They're going to give you the most basic information of what was used and where. So there are many different types of fibers. I always kind of assumed carbon fiber was carbon fiber. It's stuck to the side of the bridge, it's all the same thing. But that's not the case. Once you dive into it, it'll make your head spin. So there are many different types of fibers, knit, braided, on and on. We're not going to go into that. And maybe some of you know the difference. In addition, there are many different installation methods. Pre-cured, pre-impegged, wet layup, and many, many more. But most of what we use is wet layup. So that's what we're going to cover. So when you are using wet layup for carbon fiber, you first prepare the substrate. You apply a primer, a putty, and a saturant. You place your FRP member, which has been kind of pre-designed. You roll your FRP sheeting into your wet primer, putty, and saturant. And then you finish the FRP typically with more saturant over the top of your sheeting to kind of impregnate it on the structure. And then you spray a top coat. Seems pretty simple, just like rolling on wallpaper, but it's not. It's a lot more expensive than wallpaper, and a lot more, just like concrete or asphalt, there's many, many ways that the material can deteriorate during the installation process. Typical wrapping schemes that you see. Here's a schematic for most common shear wrapping with FRP. Most shear wrapping strips that you'll see are kind of, vertical, three-sided U-wraps. This is most common in organs inventory. Sometimes you'll see them at diagonals, but usually it's a vertical shear wrap. For flexure strengthenings, typically it's a single wrap just on the bottom flange of your girder. The full, completely wrapped, I'm not aware of any on our organ inventory, but it's probably the strongest configuration. Three-sided is going to be stronger than two sides. So when installing, surface preparation is key. Just like painting and so many other professions, surface prep is crucial to how the element or how the carbon fiber performs. You need to remove defective concrete. You need to smooth the surface. Any out-of-plane variation shouldn't exceed 1/32 inches. And most of these numbers kind of come from federal recommendations, which I'll provide a reference for at the end. And I bring this up because it's important to look for this stuff post-construction during, it's because you can always see the surface prep and get an indication of whether it was installed correctly. You need to chamfer corners. I know we have several of our FRP jobs where the corners weren't chamfered. You need a round corner so the U-wrap can actually kind of transfer stress between the sides and the bottom. A minimum of half-inch radius is recommended. Also, crack injection. Most people recommend like a 10/100ths crack injection for your minimum crack size you have to inject prior to installing FRP. However, some manufacturers even recommend injection of even up to smaller sizes. All voids larger than a half an inch should have been filled with your putty or during your surface prep. That's important. So the materials themselves, even if the contractors properly prepared the substrate, there's still so many ways that the resin can deteriorate, whether it's expired pot life, whether they've applied improper thickness, lack of adhesion, resin starved, the list goes on. So there's a lot of different ways that the resin that's generating most of the strength of the carbon fiber retrofit can, that they can screw it up. The carbon fiber itself, any deviation in alignment greater than 5 degrees in the carbon fiber is not acceptable. Waviness, dimpling, kinks, folding, broken or damaged edges, fibers, it's important to notice. And this is stuff that you can inspect post-construction. You're going to see if there's a kink in that fiber when they installed it. Just to further emphasize the point of the importance of proper prep and installation in FRP, as you can see from these numbers, the tensile strength of carbon fiber is high. It's typically 5 to 10 times stronger in tension than your most common structural steels, just A36. So it's really strong material, but it will never see those strengths because we have this very expensive, very strong material that's only as strong as the glue that's adhering it to that concrete. And the glue is only as strong as how well that substrate's been prepared. If you've got punky concrete, it's going to pull right off. So tensile strength FRP, not necessarily shear, is around the 45 KSI. So you can see that, it all comes down to the adhesive in the prep. So now I've kind of covered why we use it, most common construction, procedures for installing it. Let's go ahead and talk about defects to look for in the field. Post-installation, minor defects are minor cracking, abrasion, where there is no loss of section fibers, blemishes, chips, cuts, minor cuts to fibers, and small delams. Small delams, although my numbers aren't quite right there, typically run from 0 to 1 1/4 inches. Moderate delams are 1.25 to 6 inches, and major delaminations are over 6 inches. So this is the most common thing that, that we see in carbon fiber is delaminations. And the frequency of the delamination is important too, to notice. It should be less than 5 per 10 feet in length or width. Major defects include peeling. Any defect that's close to the edge of the FRP wrap is considered to be critical. Debonding, anything greater than 6 inches in diameter should be replaced. Cracking large and active, abrasion where you've actually lost fiber sections, cuts where many fibers are cut, and any defect, no matter the size, that is in close proximity to the edge of the FRP wrap is considered to be critical. Defects to these locations can serve as stress risers that lead to rapid delaminations and growth. In addition to that, carbon fiber is actually susceptible to alkali attack, UV deterioration, moisture absorption, high impact loads, vandalism. So it's a delicate creature. Some examples of minor to moderate delaminations, and this could arguably be a major delamination since it's at the edge of a element. You can see from the picture here, and this is pretty common, I think, from the FRP that I've inspected. You can see that the substrate probably wasn't prepared well. You see a lot of voids right on the edge of the carbon fiber wrap. So the putty, the primer, it didn't extend completely underneath the carbon fiber. From my markings there, you can see that there is actually a delamination. This is probably something that was incurred during installation. It probably hasn't grown. But you need to mark these delams and track them to see if they're getting any worse. Here's another delam on the edge of, looks like here we have some shear FRP in a U-wrap configuration going up the side of a reinforced concrete girder. We also have some flexural strip here, and the edge of the flexural strip is delaminated. This most likely caused just during construction when they didn't put enough saturant underneath the strip. Here's a delam similar to the previous where there's a kink in the fiber when they were installing it. You can see that if they would have filled that kink be with an epoxy or more binder, it could have kind of bridged that gap. But now when you have a delam, the stress transfer won't go across that delamination. So therefore you've created a stress riser. So you mark them, you date them, and you see if they get worse. Major delaminations. Here's an example of major delamination. This is actually on the Winchester Bridge, which they flew the drones on. As you can see from this picture, this structure has had lots of retrofit. We've got shear banding, and we have FRP strips. There's an interesting crack going down that you can see. I'm not sure what's going on there, but we do have an obvious major delamination. That's not very common. That's only one bridge out of everything on our inventory, and that's only one strip out of many strips on that structure. Frayed edges, it seems kind of benign, isn't a problem, but according to national federal guidelines, frayed edge is at the end of a member, and it should be considered critical, although it's fairly common. Once again, more pictures of poor surface prep, minor delaminations on the edges just from a lack of saturant. Construction overlaps, although in these pictures you don't see any problems arising from the construction overlaps, but it's an area that should be monitored. Here's another example, just poor surface prep. This is pretty common. Maybe a kink in our fiber, in our shear carbon fiber wrap here. A lot of voids. Corner delaminations. This seems like more of a kind of moderate to major deterioration. As you can see from the ground up, it kind of seems like everything's just fine. The wall of the upper wrap, or most of the U, is still in contact. However, when you have a void in the corner from just the lack of pulling the carbon fiber sheet, therefore the stresses won't transfer between the flange and the web. Boils and voids. Here's some moderate to major boils and voids. This is probably one of the worst ones that I look at for voids on the edges. Here's kind of more common what you're going to see. There's a lot of boils and voids out there. Folds in fiber sheeting, as mentioned earlier. Anytime you have a fold or kink, it's not good. Loss of primer coat. It seems like it's not a big deal, but the primer coat does have purpose. It's kind of it's protecting that carbon fiber from UV degradation, alkali attack. So it's important to at least note. Tools, visually, that's what most everybody uses. You can use a geo pick. Everybody has one, but it's probably a little heavy. Rotary percussion tool. Some of you may have used these or have these. They're actually a pretty good tool because you can extend up, so you can reach a lot of inaccessible areas and cover a large area quickly. The FLIR cameras, electrical and mechanical engineers from WashDOT, they like them, as probably most electrical and mechanical engineers do. But most civil engineers don't use them. Some people swear by them. They do have an application. Some people say that they work well, but they do have a learning curve, and they're very expensive if you drop. Quarter. Everybody's got a quarter in their pocket. Well, maybe not. Not nowadays. But if you do have loose change, that it works surprisingly well for sounding. Industry typically uses a wand. I don't know anybody that has these, but in the fabrication process, you use a wand looking for delaminations. There's more exotic tests, such as destructive pull-off tests, ultrasonics, radiography, all that stuff. There's the rotary percussion tool, in case anybody is wondering what that thing is. Actually worked quite well. Repairs are possible depending on the severity. We haven't done any repairs yet in Oregon, although we probably may have to. I don't know. Most repair will probably be done by a contractor, a qualified contractor. And briefly, we'll give kind of a debonding is the most common defect that we see. So we'll give a brief overview of kind of debonding parameters. Anything smaller than a 1/4 inch diameter, it's no big deal. Between 1/4 inch and 1 1/4 inch, you can epoxy inject it. Between 1 1/4 and 6 inches, with a frequency of less than 5 per unit surface area, 10 feet length, you can do local patching. And greater than 6 inch diameter, you should replace the material. Finally, FRP is proving to be a good design aid when retrofitting older structures for today's vehicular needs. Historically, FRP appears to have a good track record of reliability in other applications. And time will only tell the reliability of FRP in Oregon. But as the boots on the ground, it's our job to track it, since it is a critical element. So get up there close, hands-on, and track it. Here's a reference. If you're interested, they've got tons of information. I kind of robbed most everything in my presentation from them.